Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Stargazing is like going to sightseeing in the night sky, in a sense. And when you go sightseeing, you will need to make a plan and decide where to visit or what to look at. You need maps or guidebooks for navigation. And you also need a vehicle. And your vehicle will be a telescope or binoculars in our case. And you also need to prepare for the trip. And to do that, you need the basic knowledge of your trip, or the night sky in our case, and you need to prepare for the trip. First, I want to show you how the sky works, so the basics of the night sky before getting to the practical side of stargazing. Now, when you go out at night and look at stars, first thing you might notice is that stars appear to move. When you look at north, stars appear to go around Polaris or the North Star. When you turn around and look at the south, you notice that stars skim over the horizon. And this is a 360-degree view photo of the star trails. And you notice that stars coming up from the east and setting to the west seem to travel faster than the ones near north or south. Now, why do stars move that way? You may know the answer already, but it's simple. It's because the Earth rotates. So stars are actually stationary, but we're the ones who are moving. Now, with that in mind, I'd like to now introduce the concept of celestial sphere. Celestial sphere is an imaginary large sphere outside of the Earth. So the Earth spins inside of it. And celestial north and south poles are extension of the Earth's north-south poles. And you can imagine that all the stars and celestial objects appear to be stuck on the surface of the celestial sphere, regardless of their true distance. Now, on the Earth, to express the location, we use two numbers. For east to west position, we use longitude, and for north to south position, we use latitude. On the celestial sphere, it's very much alike with the Earth's coordinate system. For east to west position, we use a number called right ascension, or RA, we sometimes abbreviate. And that is measured from vernal equinox going eastward along the celestial equator. Now, this point right here is vernal equinox, and this is the position where the sun is on the spring equinox day. The blue circle, the large circle right here, is the path of the sun called ecliptic on the celestial sphere. It takes 1 year for the sun to go around once for this on this circle. Now, the units we use for right ascension are hours, minutes, and seconds. And there's a relationship that 1 hour equals 15 degrees. This comes from the fact that it takes 24 hours to go around 360 degrees. For north and south position, we use a number called declination, or DEC, we sometimes abbreviate. And that is measured from the celestial equator going north or south. And that's measured in degrees, arc minutes, and arc seconds. There's a relationship also. 1 degree equals 60 arc minutes, which is equal to 3,600 arc seconds. Now, we often use positive number going north and negative number going south for this. Now, this type of coordinate system is commonly called equatorial coordinate system. We also use local coordinate system, or observer-oriented coordinate system. And we use two numbers, altitude and azimuth, for that. Altitude is height of object measured in degrees, and that's measured from horizon. Azimuth is direction of object measured in degrees, and measured from north going clockwise. And those two numbers can tell you the location. But the important thing is, on this coordinate system, altitude and azimuth change with time. And this type of coordinate system is commonly called horizontal coordinate system, or sometimes it's called altitude azimuth coordinate system. Now, here's an example of star map for the entire night sky. As you can see, right ascension and declination are used for coordinates. Now, a large area map like this gets distorted near the poles because you're projecting a sphere onto a plane. But if you're looking at the small area map, like maybe focus on or zoom in some of those constellations, the distortion is minimal, just like the map of an arbor isn't as distorted as the world map. Next, I want to talk about constellations. The classical definition of constellations are they're the group of stars that make certain shapes, legendary shapes and things. And you might recognize some of the constellations in this picture. But under modern definition, constellations are actually 88 specific areas on the celestial sphere with exact boundaries. We often use three-letter abbreviation for constellations. ORI stands for Orion, CMA stands for Canis Major, and so on. And also, some of the asterisms that we know are not constellations. For example, Big Dipper is a very famous constellation. Most everybody, I think, knows that. But that is not a constellation. That is a part of constellation, larger constellation called Ursa Major. Next, I want to talk about the names and catalogs of celestial objects. Now, why do we need to name or catalog those objects? Simply because there are just too many of them. We can't remember them all. First, I'm going to talk about stars, names of stars, and there are many catalogs, designations available for stars, but I'd like to talk about most used one called Bayer designation. Now, most bright stars have proper names, and they are often derived from Arabic. And in this example, you see Sirius is the brightest star in the sky except the sun. And Betelgeuse is the bright red giant on Orion, and so on. Under Bayer designations, they change names. And Bayer designation uses Greek alphabet in the lowercase and constellation name in the possessive form. So now Sirius is called Alpha Canis Majoris, and Betelgeuse is now called Alpha Orionis. And normally the order of this alphabet goes from the brighter star to the dimmer star within the same constellation, but there are exceptions. Next, I want to talk about deep sky object catalogs. Now, when we say deep sky objects, we normally mean the objects outside of the solar system, but we tend to exclude single stars, so we normally mean they're like nebulas or galaxies or star clusters and things like that. Now, there are, again, many catalogs or designations available for deep sky objects, but I want to talk about two most important ones called Messier catalog and NGC, or New General Catalog, and some nicknames. Okay, Messier objects are listed by 18th century astronomer Charles Messier, and he was a comet hunter, and he made this list as objects not to look at because those objects confused him with comets he was looking for. And there are more than 100 objects listed in this list, and from M1 through M110. And they are very bright, so they are all observable with small telescopes. NGC, or New General Catalog, is another widely used catalog, and that is compiled by an astronomer, J.L.E. Dreyer, based on the works of Herschel's. Herschel's famous astronomy family, William Herschel and his son, John Herschel. And there are more than 7,000 objects listed in this catalog in the order of right ascension. And that includes objects seen from southern hemisphere, whereas Messier object includes only the object that can be seen from northern hemisphere. And most Messier objects also have NGC numbers. Next, I want to talk about nicknames. And we like nicknames because they are easy to remember, and we love them. Here's some examples of nicknames of some objects. And they are normally named after their shape or location or characteristics. Now, with that knowledge, we should be able to read the star chart. So let's try it. Here's the constellation named Cygnus. Those yellow dashed lines are constellation boundaries. Here's a star named Deneb. Here's another star name under Bayer designation called Beta Cygni. And there are some Messier objects seen in this map, and also NGC objects seen here. Next, I want to talk about magnitude and size of the celestial objects. When we talk about magnitude, we normally mean apparent magnitude, not the absolute magnitude, the amateur astronomy. Apparent magnitude is an indication of how bright the object looks, not the true brightness of the object, so not to confuse with that. So for example, if you see a magnitude 0 star and magnitude 5 star, by definition, magnitude 0 star is 100 times brighter than magnitude 5 star. So the smaller the magnitude number is, the brighter the object is. And also the magnitude difference of 5 equals the brightness difference of 100 times. Now, if it gets brighter than magnitude 0, we use negative numbers. Now, how bright is magnitude 0 star? It is about as bright as 100-watt light bulb placed 4 miles away. Here's some examples of apparent magnitude. Vega, it's a bright star in the constellation Lyra, is about magnitude 0, so we use that as a reference in this example. And Sun is about magnitude minus 26.7. And Sun is 49 million times brighter than Vega. Full moon is 100,000 times brighter than Vega. On the fainter side, the faintest star under ideal condition you can see with the naked eyes is magnitude 6.5, and that's about 400 times dimmer than Vega. Next, I want to talk about the size of the object. Again, when we talk about size, we mean not the actual size, but angular size or the apparent size, how large the object looks. So we use angles to express that number, degrees, arc minutes, and arc seconds. Here's some example. This is a photo of the moon and Saturn. The angular size of the moon is about ½ a degree. And as you can see, Saturn is much smaller than the moon. It is actually, the size of the disk is only 20 arc seconds across. On the other hand, some objects are really huge. Like this is the photo of Andromeda Galaxy with a composite photo of the moon to compare the size. And the size of Andromeda Galaxy is 3 degrees across. This is a huge object. You can quickly estimate the angles on the night sky just by extending your arm like that and look at your pinky, and that's about 1 degree. Your fist is about 10 degrees and whatnot. You can try it for yourself. Okay, now I want to talk about the practical side of stargazing. I'll show you how to find the object and tell you something about observing conditions and preparation. The classical method of how to find objects is to use star maps and follow the constellations and find the bright stars and manually find the objects that you're looking for. And in order to do that, you need to know a few major constellations at least and some bright stars. And it may take time to do that at the beginning, but you will learn the night sky much faster this way. There's another new, quick, and easy method available, and that is to rely on the computers. There are a lot of go-to or push-to telescopes available nowadays, and you can also use Starfinder product for that. But in this talk, I'm going to stick with the classical method, and I will show you how to manually find objects. Now, the first thing you want to be able to do when you get out is to orient yourself. You want to know which way is south, north, east, and west. The easiest way to do is to find Polaris or the North Star. And it can be found easily from Big Dipper or Cassiopeia, whichever is visible. And then once you find north, then south is behind you, east is to your right, and west is to your left. So next, you want to be able to identify which constellations are visible, which ones which. And again, in order to do that, if you know a few constellations and bright stars, that would help. But you can use a specialized star map called Planisphere. I have an example here. What it does is it will show you which constellations are visible on which direction at certain date and time. So this is very useful, especially when you're starting out this hobby. Okay. You want to next select your targets. And, the guidebooks, a lot of guidebooks or star charts will show all the targets you can look at. We have some examples of guidebooks over there. And it is also a very good idea to make a list of targets before you go observing session. When you're actually using the star map to find objects, the good rule is to start in a wider area and then zoom in. Here's an example to find an object in a small constellation Lyra. Now, first you want to use a map like this, the large area map like this, to first find this constellation. And then you want to zoom in, maybe use a separate set of chart and look into the detail to find the object. You want to use finder and the low power eyepiece. This particular type of finder, what we call unit power finder, is very useful in this process. What it does is it projects certain shape, like red circles shown in here, against the background. I have a couple of examples of those finders. Here's two of them right in here. And what it does is you attach that to the telescope and look from like here, and then you'll see the red circles against the night sky. And what you have to do is just aim that red circle to the target where you're looking for. You can also use geometry method or star hopping method, which I will explain in the next couple of slides. Geometry method uses simple geometric shape to find a hidden object in the night sky. I'll show you an example to find Whirlpool Galaxy, or M51, in this night sky. As you can see, this is Big Dipper, and this galaxy is located near Big Dipper around here. You can see a little circle. You can see the location on the star map, but you cannot see it on the actual night sky because it's too dim for your naked eyes. So what you have to do is, by looking at the star map, you make an imaginary triangle like that, and then project that triangle into the actual night sky and place your finder at the apex of this triangle, and you should be able to find the object. And this is called geometric method. We also use star hopping method. And I'll show you an example to find Andromeda Galaxy in this sky. Here are some constellations and asterisms seen here, Andromeda and Cassiopeia and the Great Square of Pegasus. And this galaxy is actually located here. Again, you may or you may not see it with the naked eyes, but under light-polluted sky, you won't be probably able to see it with the naked eyes. So what you have to do is, in this particular example, is to find the Great Square, and then find this star connecting the Great Square to Andromeda. You hop once to find another bright star here, and hop again to find this star, and hop this direction now to find this star, and extend exactly the same distance and direction to find M31, or Andromeda Galaxy. So in this example, you hop from one star to the other, and that's called star hopping. Next, I want to talk about conditions that affect stargazing. Again, there are many different conditions that affect but I want to talk about 4 of the most important ones: light pollution, transparency, seeing, and moonlight. Light pollution is excessive or unwanted artificial light. It is a side effect of our civilization. And we have 2 types, local light pollution and general light pollution. Local light pollution is unwanted nearby light. Here's a photo of downtown Ypsilanti, and you don't want to stargaze in a place like this because there are too many bright lights around you, and you won't be able to dark adapt, and it will be very difficult to see celestial objects, especially the dimmer ones. Now, on the other hand, general light pollution is actually a brightened background of the night sky caused by city lights, which we call sky glow. Here's a photo of Orion taken from 2 different skies, and as you can see, the background is pretty much brightened and the light polluted sky. Now, this brightened background or the sky glow washes away the contrast, so especially for dim objects, it will be hard to either detect or see the details of it. But if you're looking at some bright objects like the moon and planets, it doesn't affect as much. You can see the moon and planets on the light polluted sky also. Here's a light pollution map of North America. Yeah, as you can see, eastern half is fairly highly light polluted. Here's the light pollution map of Michigan, lower Michigan, and we are in this white patch, another area, and we're in the highly light polluted area. As you go away from the cities, from the white area to red and red to yellow and so on, you will notice that the quality of the night sky improves dramatically. And the observatory we go, the Peach Mountain Observatory, is in this orange area. And also, we have wonderfully dark skies in the northern part of Michigan. We sometimes go out there to make trips just to have the good quality sky. Okay, next is transparency. Now, transparency is clarity of atmosphere. And we want transparent, good, clear sky. If the transparency is low, the light is blocked. Light from the object is blocked, so it will be hard to see. And also, it reflects the city lights, so it worsens the light pollution. The other factor is atmospheric stability, or what we call seeing. And under turbulent sky, as you can see on this example, the image gets really blurry. Now, when you're starting out stargazing, you can get information from different sources. There are a lot of star maps or guidebooks, magazines, and different books available. You can go to the local library or a local bookstore. You can get some astronomy softwares, and the good news is some are absolutely free. And what I like to do is make custom star charts before going out observing. And also, nowadays, websites post all kinds of information, useful information, weather and sky conditions, information for planets and comets, and so on. So yeah, you should go and look at those.
Okay, first I'd like to just go over how our eye actually works, and sort of a little eye anatomy 101. And as most of you recall, there's a simple lens here in the front of the eye that projects an image back here on your retina. And the retina is coated with light receptors called rods and cones. And then ultimately, the retina is connected through the optic nerve to the brain. Rods and cones don't work the same. At night, we tend to use rods and we use our cones less. And the reason for this, as you can see, if you look at this graph, you notice that this is like our retina laid out here, this side being toward our nose and the other side toward our temple. And your y-axis is your density of receptors per area. You'll see that the rods start out and build up here to a peak. You see the same thing going on the other side. Cones, on the other hand, start out on the edges almost non-existent, rise to a sudden peak, and then drop off just as suddenly and are almost non-existent again. Our best visual acuity and where we see color is in this area right here. You may notice that where the optic nerve connects, we actually have a blind spot. Now at night, we're going to use the rods more than the cones because rods are much more light sensitive and they pick up motion better. And we're not going to tickle those cones enough to see color anyway. So at night, we also tend to develop a secondary blind spot right in this area. So to put a spin on that, use a thing called averted vision. And what that really means is that when we get a target in the scope, we don't really look so much directly at the target, but we look slightly off to the side of the target. And what that does is places that image more on the area where our rods are located and less on the cones. And I've tried to demonstrate this here with a little dramatization. This is a picture of M13 that would be reminiscent of a pretty decent night through a medium aperture scope at least. And this would be like if you were looking directly at M13. But as you start to look off to the side of M13, we place that image over on the rods more, and then suddenly you see a brighter image and you see more detail. You'll also note this little galaxy up here, how much brighter and more detail that you now have with that. Now again, this is kind of a dramatization, but when you get this down right, the effect of it is pretty much similar to that. And then we have to go through this process called dark adaptation, and that really is two different steps. The first one is our pupil simply dilates and allows more light to enter the eye. And our pupil opening, or aperture, for a younger person is only about 7 millimeters. As we get older, that tends to diminish. I might be down to maybe 5, unfortunately. And then maybe more importantly, as we go through a chemical change in the retina, which increases our light sensitivity further, and at the same cost of color perception because we're not using the cones so much. You can kind of see that effect if you go out in a parking lot at night. As you dark adapt, you'll still be able to see the cars, but it'll get much harder to tell what color they are. This chemical adaptation takes 20 to 40 minutes, depending on how dark the environment is around us. So we're real sensitive to bright lights, particularly white light, because just a glimpse of it and we're destroyed and could be all the way back to 20 to 40 minutes again. The redeeming quality, though, is that red light doesn't seem to be so destructive. And the reason for that is if you look at this spectrum of light, you'll see that blue cones have a peak, green cones, and red cones, and about where you'd expect them to be. Your rod cones, or rod sensors, have a peak right here. Now, they don't see color, but they have a maximum sensitivity in this kind of blue-green area. So if we use red light in this area, you'll notice that the rods, if you follow this curve down, are almost non-existent here, so we're not messing those up. But our red cones are still active here, so we're able to see what we're looking at, and we see it as red. We go back to the telescope and start using the rods and not the red cones, and therefore we really haven't destroyed our night vision. And then ultimately, this signal is sent to a little computer we all carry around called our brain. And the brain's rather fascinating because it actually can correct optical faults in our eye. One of those is being a color distortion that we have because it uses a simple lens in the front. Another interesting thing is that image, as it's projected on your retina, is actually inverted. It's upside down. But I'm curious, does anybody in this room see me upside down right now? That's good. So the brain actually makes those corrections for us, so we can actually train our brain to actually use our eyes better as we get more and more into observing. And the other cool thing is, since we've invoked a computer now, that in turn can mess up and screw up our vision and gives us the entertainment of optical illusions. And consider that as that image is hitting your retina, there's only white dots there. The rest of it is all in your brain. So why do we need telescopes? Well, as I mentioned earlier, the aperture or opening of our eye is only 7 millimeters at most, and that doesn't gather a lot of photons. And the more photons we can gather, the brighter our image is going to be and the more detail we can see in it. An analogy is if you considered all of these little raindrops as photons of light coming from the sky or the object we're looking at, well, would you gather more photons with this cup or with this bowl? Same way, would you gather more photons with a 90 millimeter refractor or a 24-inch telescope? So basically, we need more light gathering ability. And all telescopes, regardless of what size they are or what type of design they are, really do one thing. and that is that they gather and concentrate light down to a little point that will actually still fit through our pupil. And we do that with telescopes. The first scope that was invented was called the refractor, and this is the type that was used by Galileo. It uses a lens here in the front, which simply bends this light back to a focal point. It produces an inverted image, just like our eye lens does. But you may notice one of the inherent problems in a simple refractor is not all of these wavelengths of light are deflected by the same amount, so they don't reach the same focus point here. So to help mitigate that, we came up with, in this case, an achromatic refractor. And this would be the simplest type to do this correction. And really, it works by using two pieces of glass, a crown glass here in front and flint glass in the back. And the magic of this is that crown glass bends light incorrectly in one direction, flint glass bends light incorrectly in the other direction. So, I guess in amateur astronomy, two wrongs can actually make a right. Anyway, the second type was a Newtonian reflector invented by Isaac Newton and called the Newtonian for that reason. The difference here is rather than a lens, we have a parabolic mirror located in the back of the telescope. Light enters through the front, hits that mirror, reflects back here to a secondary mirror, and then back up to an area where we can actually place an eyepiece and view it, since we wouldn't want to stand here in front of it. And one of the things about a reflector is it has no chromatic aberration because it doesn't use glass. But nothing's perfect, and reflectors have their little issues too. One of those being is that because of this little central obstruction here, this blocks a little bit of a light that can hit your primary mirror and causes somewhat of a loss in contrast. These telescopes also invert your image and have the aggravating quality of doing a mirror reversal on it as well. And then there's another type of telescope called compound scopes that use a lens and a mirror, and these tend to be our most compact telescopes for their aperture. So ultimately, we need something to actually view that object, and this is where we use eyepieces. And an eyepiece really works like a microscope. Again, we have our objective lens. As you saw in the tank over there, our light converges to a focal point right in here. And then the eyepiece actually magnifies that little image that's formed right there. And the focal length of the eyepiece, which is the distance between this image and the actual eyepiece, is what determines the magnification. And as you'll see, once again, these beams diverge again, but not so much that they won't fit through our pupil and form the image that we want to look at. Eyepieces vary considerably in their apparent field of view. That would be like the circle of light that you'd look through when you look through it, how wide that area is. They vary from very narrow to looking like you're looking out a spaceship window. And there are some types that are suited for better objects than others, and certain eyepieces work better in certain types of telescopes and sizes of scopes. So therefore, we have justification to spend money collecting a lot of them. Oh, so that's what happened to my budget. Anyway, this is a picture of my collection from about 3 years ago, and it's, well, it got a little bigger since then. But the truth of the matter is, for any given telescope, 3 properly chosen eyepieces will really pretty much do the trick for you. And there's a few consequences and truths about magnification. One of those is that a lot of times people think we use huge magnifying factors, and we really don't. Rarely would we exceed 200 or 300 times, and more typically, probably 25 to 150. Magnification does increase the size of our target, but at the cost of decreasing its brightness. But there's one redeeming quality, and that is it also decreases the brightness of the background around the object. A magnification will also magnify any faults in your telescope, and it'll magnify faults in the atmospheric conditions. So the moral of the story is we use the magnification that best frames our target and provides the best contrast that the current conditions will allow. And to give you a little example of how this works, this is M31. This doesn't come out as well as I had hoped. In a very low power field, and you see how you can see the full width of the galaxy, 2 satellite galaxies here. As we increase the magnification, you'll see this one drops out of the field of view, but we don't see the entire galaxy. We see the center area a little more, but in this case, this is probably the more pleasing view at the lower power. This is the Orion Nebula, known as M42. You'll note in this picture, going to the higher magnification increased the darkness of the background a little bit. You'll see the central area here larger, but this was probably under a little shaky seeing conditions, and some of this fine nebulosity that would be down in here is actually starting to wash out. And then some of the tools that we use, one of them are filters, in this case color filters, and we use those to enhance certain details on planets. We're going to see a demo of that in a minute. We use moon filters to knock down the brightness of the moon because it's usually overwhelming. And even better than that is a polarizing filter, because that can reduce the brightness and reduce glare, and it's much easier to see fine detail. And then one of the real miracles in filters that we really appreciate are light pollution or nebula filters. And these don't actually make an object brighter. They work by making the background darker, therefore increasing the contrast and making the object look brighter. And it's very convincing. You'd put money on it that object is brighter, and it really isn't. And the way those really work is if you see the spectrum of light, you'll see what our nebula filters do is they concentrate on this band of light and also over in this area. What they avoid is this area through here, because all these bands are from sodium, mercury lights, general sky glow. Now in reality they do spill a little bit into these areas, but most of them are down here. So you'll see that these filters aggressively block these bandwidths. And in the case of a narrow band filter, they're so aggressive, they'll actually take these little slices out of these bands here, transmit those, and block everything around it, again causing that background to get darker and making the object look brighter. These work so well that sometimes it could make a difference in whether we see an object at all. And then probably the most important filter that we use are solar filters. And as you can see here, we've got to make sure that they're always in good condition, make sure they're solidly attached to the front of the telescope. One of the types we commonly use is one that basically looks like this. You won't see any light pass through that because they're very aggressive, and it would attach onto the front of the scope and has tape here to make sure that's held on there firmly. So make sure they're attached good, they're in good condition, and you never want to view the sun without one of these. And oh, we have some fine print, because otherwise it could be the last thing that eye ever sees. So with that, I'd like to do a hot demo this time. First one is to give you an example of how planetary filters work. We have a actually rather nice Hubble shot of Mars displayed here. And what I'd like to point out is that if you look in some areas, particularly along in here, you'll see there's actually some faint cloudiness there that's really kind of hard to see. You'll see some darker areas, some brighter areas, and what will happen is if we slide a red filter, or this could be orange in place, you'll see those dark areas get much easier to see. But the clouds and some of the white or lighter areas actually are considerably diminished. On the other hand, if we were to use a blue filter, we'll have somewhat the opposite effect. You'll notice the polar cap is brighter. And remember those clouds I pointed out? Well, look how much they're popping out now. Again, kind of in that central area. So that's basically why we use color filters, to enhance certain details. And then we have solar filters. So what we've done here is we've kind of mocked up an artificial sun, which we're just going to start up here. And we've got shields here because this is so bright. When I crank it up all the way, you do not want to look directly at this. And then we have a mirror here which is reflecting the light back over to your telescope mirror. And then we have an eyeball back here which Warren has cleverly painted like an eyeball, including some bloodshot eyes, which maybe many of us had this morning. I did when I woke up. And then in the center here we have a solar filter. In this case it's actually an infrared filter. And you notice this is in front of our mirror. In reality, it wouldn't be placed here. This would be the front of the scope, and of course your eye would be well outside of it, but that's really too difficult to set up. So what we're going to do here is try to actually mimic the sun. And we're going to crank this up. And again, we have a solar filter in place, so we're safely looking at this. So this is your eye looking with a solar filter. But whoops, that filter wasn't attached very solidly, and it just fell out of place. And oh, geez, that must have hurt. Moral of the story, please use a solar filter. So then we need something to actually hold the telescope, and this is called a mount, and they come in two basic flavors. One of them is an altitude azimuth mount, or we shorten that and call it an alt-az. And it has basically two simple motions. This actually is a telescope in alt-az mode right now. And if we move this direction, we're moving an azimuth. And again, we break to what Yasu had said about finding our way around the sky. And we can move an altitude. So altitude and azimuth. Now, an equatorial mount, on the other hand, has the advantage that it compensates for the tilt of the Earth's axis and allows us to actually track objects. And we can do the same thing here if we simply take this mount and we tilt this such that we are actually angling this. So if you imagine an axis coming up through this way, going up along the forks, that would be oriented toward the north celestial pole. And now what you'll see is we have this same motion here, which is now called declination, and we have this motion, which is now called right ascension, and that motion will actually track stars. Once this is aligned, I don't have to worry about declination, only this. There's a little motor in here, so we turn that on, and it tracks for us. No matter what type of mount that you select, you've got to make sure that it's capable of solidly carrying the weight of the telescope you're putting on it, and it's steady. You don't want to have the image shake every time the wind blows a little or you're even refocusing the scope. And then finally, there is a type of telescope that really doesn't need a mount at all, at least in smaller and medium sizes. And it's really like two telescopes side by side called binoculars. Binoculars have some advantages. One is, unlike refractors and reflectors, they don't turn your image upside down or mirror image it. You look at the sky, when you look with the binoculars, everything's oriented just the way it should be, except it's magnified and you can see fainter objects. So that's a real advantage. They have the advantage of no setup being required. They're very portable, and they provide a very wide field of view. In fact, for many objects, like M31 being one of those, sometimes binoculars actually give us a better view than what a telescope would because of that wide field. And really, for all of those reasons and probably more, we highly recommend binoculars for starting out for beginners.
There are a wide variety of different objects that you can see with amateur equipment. And over the next few minutes, I'm going to show you some of the different types of objects that you can see either with a telescope, binoculars, or the naked eye. We're going to start with the solar system. The solar system has the sun. There are 8 planets, 9 if you include Pluto, and a variety of moons, comets, asteroids, Kuiper Belt objects, and so forth. But of all of that, the first thing that most amateurs look at through a telescope is the planet Saturn. And this is a typical view of the planet seen through a telescope, except the moons are not visible in this photo. This is another view, and probably a little bit better view than most people will see. This is the planet Jupiter. You can see the disk of Jupiter, along with the 4 moons, Io, Europa, Ganymede, and Callisto. And this shows 2 sketches of Jupiter. Again, probably a little bit better view than most people are going to see. And as Charlie showed you earlier, you need to have a solar filter to look at the sun, but it's very easy to see the sun with the proper equipment. You can see sunspots and solar flares. The moon is a nice target for people to look at. If you have a pair of binoculars or a telescope, you can see craters or occasionally mountain ranges. The actual appearance of the craters varies depending on the phase of the moon. Next, we have comets. Now, I'm not going to spend much time on this, but comets have these peculiar naming convention. The first one is the naming convention used for Comet Halley, and the second one is for Comet Lulin, a comet that's currently visible. Every few years, you have a very bright comet, and this was a comet visible 12 years ago, Comet Hale-Bopp. But not all comets are that bright. Some comets you need to have a pair of binoculars or a telescope to see, and this is a view of Comet Lulin I mentioned a moment ago. And next, we like to look at stars. Stars often come in pairs, double stars. The best known double star is Mizar and Alcor, which are located in Ursa Major. Albireo is a pair of stars that's colored. So you have a yellow or blue, or as we often refer to it as Mason blue. And on the right, you have a multiple star system, Rho Ophiuchus. Stars come in a variety of colors, but often the colors get washed out when you look through a telescope. There are a group of stars that are bright red called carbon stars, and this is an example of one carbon star. Now, as Yasu had mentioned earlier, there's a category we call deep sky objects, and there are four main types: nebula, open clusters, globular clusters, and galaxies. Now, before I go through that, a lot of you have probably seen photos of objects either in books or on the internet. And along the top, you can see these very colorful views. But if you look through a telescope, you're not going to see those colorful, bright views. So on the top, this is a view of M57, the Ring Nebula. But this is what you're more likely to see through a telescope, much dimmer and not as colorful. And again, a bright image that you might see in a book, but the corresponding image you see through a telescope. And a third example, M101, a spiral galaxy, but the corresponding view you'd see through a telescope. And here's just a variety of photos. This was North American Nebula, NGC 7000. The Orion Nebula, this was heavily processed image. And here's just a variety of emission, reflection, and dark nebulas. This guy right here, the Horsehead Nebula, is a dark nebula superimposed on another nebula. And a group of planetary nebulas and supernova remnants. The next category are open clusters. The nearest and probably best known open cluster is the Pleiades. Pleiades is visible naked eye, but probably better viewed through binoculars. And most people can see 6 stars if they look at the Pleiades naked eye. Open clusters come in a variety of different configurations or shapes. This is just another open cluster. This is one of the brighter globular clusters, M13 in the constellation Hercules. This shows a pair of galaxies. M51 is the guy right here, and then there's a small companion galaxy, NGC 5195. And this is an elliptical galaxy, 59. And just a few other photos of different galaxies. Now, if you observe from a dark location, you may be able to see a band of light across the sky. And this is the disk of our own Milky Way galaxy. This just shows 2 views of the Milky Way galaxy. And there are 2 other topics I'm going to go through here. Occasionally in Michigan, you may be able to see in the northern sky colored lights. And this is called the aurora, sometimes called the northern lights. Commonly, aurora are red and green, but occasionally you may see pinks and purples. And they come in a variety of shapes. And on the right, you see a flame aurora. Aurora can be forecast, that it's not 100% predictable, but there are these forecasting services. This is a slide from the University of Alaska at Fairbanks. There's also another service from spaceweather.com. And this shows a typical pattern where the aurora is mainly concentrated in northern Canada and Alaska. But occasionally, you're going to have the aurora come further south, either into Michigan or Oregon. And if you make use of forecasting services like this, it increases the chance you'll actually be able to see them. So if you know it's likely to occur, then you can go out and look for them. And lastly, when people spend any time out at night, from time to time they may see these streaks of light across the sky called meteors. Now, meteors occur more commonly certain times of the year. For example, you see these peaks, and there's a peak right here, and this is at August 11th and 12th of each year, you have what's called a Perseid meteor shower. And if you observe from a dark location after midnight, you can reasonably expect to see 1 meteor per minute. And there are several of these meteor showers over the course of a year, and you can see these different peaks here. Now, this is in fact an average over several years. And this little peak here called the Leonid meteor shower is a case in point. It was very active a few years ago, but is decreasing in activity.
I'm going to talk to you about our community involvement, and part of that community involvement is bringing astronomy back to the streets of Ann Arbor in the metropolitan area. This particular event we're hosting here was set up to view the planet Mercury across the sun. And you can see we've got a filter here. I think that's pretty understandable with the demonstration we had of why we use solar filters. Now, back to the Ann Arbor campus, we participated in some other events with the university, and you can see we have another telescope set up, but this time it was set up to observe sunspots, and you can see the filters up there again. Once again, now, as Dave talked about the Leonids meteor shower, we also hosted a public program for the general public and a Girl Scout group to get their astronomy badge. So we had one of the things we did was a comet making demonstration, and you can see the gas and dust we created to show this demonstration. And this was followed with an observing session that we did for the group, also to look at 4 meteors, but also do some deep sky observing too. Now, back to Angel Hall down on State Street, you can see here the sun setting very low on the horizon. And this is the transit of Venus, where Venus crosses the surface of the sun. Once again, you can see some of these scopes over here do have solar filters, and you can see some people are using these little eyeglass solar filters. Another important event we held was with the Science Museum. As you can see, we have a special telescope set up to view the sun and look for solar flares. Now, during some of these lectures, we often get into explanations of looking at solar flares and what the general public is actually looking at. So we work with the parents and children. Now, if you look at this particular telescope we have right here, you'll see the same telescope right here in the front. This is what's called a personal solar telescope. And it's a very nice instrument for looking at solar flares and things of that nature. And that's specially designed too with a different type of filter. Now, another event that we host every year, we are co-sponsors of Astronomy at the Beach. Some of our members have actually given lectures here. A lot of us bring our telescopes here, and you can see it all set up here at Kensington off the beach, and that's why they call it that. It's really a nice event. It's something that you can go with your family or your grandkids. Another project that we did, this camp is actually owned by the Hazel Park Community School District. They asked us to come out and do an observing session for their science camp. We are part of the Night Sky Network, and the Night Sky Network was developed by the National Aeronautics and Space Administration as its public outreach program. What they have set up is a series of outreach kits used to demonstrate the relationship between the Earth, the Moon, and the Sun. And they're very basic and they're very easy to use, but they help get a lot of these concepts to the general public. See, another one we did was using the Earth, was a demonstration of its relationships to lunar and solar eclipses. Again, we also use these outreach kits, public observing sessions, working with the general public and parents. A couple of our members have actually built portable planetariums. As you can see here, here's the projector down here. And they've taken this to various events, and it's been very well received. Here's the other portable planetarium. And children enjoy it. They like going inside and seeing the night sky, and it works out to be very enjoyable for the group. Now, as was mentioned before, we are part of a very unique arrangement with the University of Michigan. Here is an aerial view of Peach Mountain Observatory. Here's the 85-foot radio telescope, and some of you may have been out there and seen this telescope. Here's the 24-inch McMath telescope in the observatory. This telescope was installed on Peach Mountain in 1959. It was originally moved from the McMath-Hulbert Observatory on Lake Angeles. Here's a map of the overview of the Peach Mountain Observatory. Here's North Territorial Road, and this is the entrance road that goes up, Service Drive. There's a small asphalt road here, general parking, and then this is a dirt road going to the observatory. Now, the telescope itself is a 24-inch Cassegrain. You can see this tube assembly. This tube assembly is approximately 10 feet long. Here's the 24-inch mirror at the bottom. And this type of design has a secondary mirror up here and reflects the light down to the bottom of the telescope. From on top of the observatory, looking down, we have a 46-inch diameter right ascension drive gear. Here's the declination gear in drive. And this is very similar to right ascension declination that Yasu talked about and the equatorial mounting that Charlie talked about. Now, how do we do all this and maintain the observatory? We do have work groups, members that volunteer their time on mechanical, electrical, and optical issues that need to be taken care of. Some of the mechanical issues over the years were just installing a new drive motor. At one time, there are 3 or 4 of these motors, and they do fail, and they do have to be repaired. We did have a big electrical upgrade in 2008. One of our members redesigned this entire system, and it improved the positional accuracy and tracking of the telescope and eliminated some reliance on some of the other drive motors, which was very important. Also, we continually have the mirror recoded, but this takes 3 or 4 people to do. And the reason it does is that mirror weighs 135 pounds, and we move it carefully. We also have training programs for our members so they know how to use the telescope and how to use the observatory. Now, this is some of our observing in the summer. You can see we have that short sleeve, but we do contend with some mosquitoes at times. Then again in the autumn, it's a little cooler, a little nicer. See a couple homemade telescopes here and some other commercial telescopes. Winter. Yes, we do participate in the winter, and we do shovel that snow so we can go out there and observe. And back in the spring, you can see the observatory in the background. We had some telescopes set up. These are some of the other types of telescopes that Charlie and Yasu talked about. But what we would like to do is invite you out to Peach Mountain. The entranceway is off North Territorial Road, and you can take it off Dexter Pickney Road. You know where Dexter Pickney Road is? About a mile down the road, you'll have the entrance. And if you want to know more, you can go to the Lowbrow website. And also, there are no restrooms at the observatory. And secondly, if you want to continue to know more, just go to this website. It's also listed on our brochure.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. Remlois Tiffany Endowment, and by gifts from friends of the program.